So this thing that you did with Judy on Monday is a thing that they developed at James Madison University, which is where she used to teach. It's just a way of kind of getting some feedback from students at kind of the middle of the semester, so that I can alter what I'm doing. We can figure out ways of dealing with things that you guys are having troubles with. And one of the overriding things that kind of came out of that was you guys are concerned about pace, and she wasn't sure if it was pace of the class in general or pace of live coding or what it is about pace that seems to be going too fast. So if you guys could tell me, is it the pace of live coding? Is it the pace of the course in general? What's the deal with pace? Don't shake your head at me, Chance. Like from your conversations with your peers, what seems to be the issue with the speed? It seems like I'm going too fast through things. What part of it is it that needs to slow down, and what way does it need to slow down? Okay, so what's too fast about it? Just me going through it, or does it come? Am I not explaining what's going on clearly as we're going through it? Like, what is it about the pace of live coding that's too fast? You guys can talk freely. Because I want to do live coding in a way that's beneficial to you, because it doesn't serve me or you to go through live coding in a way that doesn't help you figure out what's going on. Oh, okay. Well, that's not really helpful. It is 50% of the class. I was hoping that everybody would be here. I'm curious as to why everybody's not here. Well, maybe we should do this debrief when everybody's here. Um, There were two comments about pace. One was comments about the pace being too fast, but then there was another comment, and I don't know if this was an isolated comment, about when the pace does slow down, you lose focus. So, for example, when I'm helping somebody deal with an issue because their code is bogged down somewhere, it is easy to lose focus, especially if that becomes this protracted kind of long thing as I'm trying to figure things out. And one way to not lose focus, to kind of remain in the moment during that, is while I'm dealing with somebody else's code that they're having trouble getting past a certain point, ask yourself, you could ask yourself two things. One, when's the last time I annotated the code that we're currently working on? And then during that dead space, go back and go through and make annotations, because I suspect that your code is pretty much like my code when I'm live coding. It's kind of sparse in terms of annotations, like what am I doing? Why did I do it this way? And those annotations are really helpful when you go back and have to do some scripting on your own. The other thing that you could do, if you exhaust that avenue for kind of staying in the moment, is ask yourself, okay, what's the next thing that I would do in this analysis? What's the next thing that I would want to do? Is it making a graph? Is it trying another type of thing to do with the data or whatever? And ask yourself, what is that next step? And can I start making progress on coding that myself? Uh, that then keeps you definitely in the moment. But the other thing it does is it gets you out of the habit of just waiting for me to show you what the next portion of the script should be. It gets you thinking about how to go about scripting yourself. So fill those dead spaces when things have kind of bogged down because somebody's having difficulties, and say, okay, can I improve my script that I currently have by adding annotations so that I know what I was doing and why I was doing it? And what's the next thing that I suspect that we're going to be doing, and can I start making progress on that? And what you'll find occasionally is that you learn as much from taking what you already know. So, for example, you've learned some things about the syntax of R, and saying, okay, I know this much about R. How far can that carry me? And we'll see this with ANOVA. The syntax for ANOVA is very similar for a one-way ANOVA, a two-way ANOVA, a regression, an analysis of covariance. The syntax is very similar, such that when we get to the two-way analysis of variance, which is the next thing we'll do after this, um, I'm not going to give you the code. I'm going to ask you to give me the code based on what you kind of already know about the syntax of R. Can you figure out what would be the syntax for setting up a two-way analysis of variance, something with two treatments, rather than a single treatment, can you figure out what that syntax is? So, oh, that is somebody. So anyway, we'll proceed. Who has Macs here? Only two of you. Well, darn it. Would one of you be willing to share your code on the screen for running summary SE and making a figure, which is what I asked you guys to do for today? I can unshare my screen. Hayden, are you drawing the short straw? Are you drawing the short straw again? Okay. All right. So have you run your code all the way down to this point? Okay. So, oh, it says it's connecting still? Okay. All right. So can you blow up your text so everybody can see some? Oh, crud. Why is that one not on? I didn't even notice that because it's behind me. Well, I would love to turn it on. How did turning this one on turn the other ones off? All right. Okay, so that's bigger now. So what you've got here, let's see, where are you at? Show us your code where you've worked. Nope, so, yeah, your work, yeah. So we've got summary SE. Summary SE is just a function within the package rmisc. So whenever you need summary SE, you should make sure that you always load up rmisc. So summary SE is a function that somebody wrote a number of years ago, and for a long time it wasn't incorporated into any package, and so you just had to know that it was out there. You had to copy it and save it somewhere on your own hard drive, and then you would plunk that whole chunk of code into anything that you were doing if you wanted to try and summarize your data in terms of means and standard deviation, standard error, and 95% confidence intervals. So now it's been incorporated into a package, so you can just call it up if you have that package loaded. So you have to tell it what the data frame is that you're working on. You have to tell it what the measure variable is, and you have to tell it what the group variable is. And in this case, it's transdat and treatment. So run this line so we can see your output. Oh, there it is right there. Oh yeah, so here it is. Tells you that you have control, 2% glucose, 2% fructose, a 1-to-1 mixture of glucose and fructose, and 2% sucrose. You have 10 observations of each. These are the averages. These are the standard deviations, the standard errors, and the confidence intervals. And you still see that the confidence interval is somewhat bigger for the control than the other ones, but it's not so big that it violates the assumption of the homogeneity of variances assumption. So now that you have that, the next thing I asked you to do was to create a graph. And so you're calling it graph one. So you've assigned it using the assignment operator to a tag. You're using ggplot. You're using data from dat. You're using aesthetics statement to define what the x variable is and what the y variable is. You're using geom bar, you're using theme classic, and then you're changing the angle and justification of the text. So what does that graph look like? Call that up for us. Okay, so this gave us a bar graph. And two things about a bar graph is bar graphs are usually used I usually use them for count data because as you count something up, you might think of that thing as filling a bin, as opposed to this is growth and it's a rate essentially. How fast is something growing? So I typically use bar graphs to illustrate things that have mass in a sense, and I use points to refer to things that don't have mass in a sense. So I probably would have done a gm underscore point and then define point. But what's the other thing that I asked you to include in your graph? Not just the means. This tells us what the means are, right? And get rid of that stat identity thing. It's not going to work with gm point. That's a bar graph thing. But you still need the parentheses. So run that now. Yeah. Ah. Here's the problem. What have we not done correctly here? And I should have seen this when I was going through your graphing statement here. And now it's really obvious because you used point instead of bar graph. Nope. It's showing you every data point. 1, 2, 3, 4, 5, 6, and then there's some overlap. 1, 2, 3, 4, 5, 6, 7. These are the actual data point. You don't want to be graphing the data points. You want to be graphing what? You want to be graphing the mean. So how can we do that? Go back up to your summary SE. Oh, right here. So what can you do to store that information that summary SE outputs so you can come back and grab it? Just use the assignment operator and assign it to something. I usually use summary SE and I always assign it to CI plot because I'm always doing this because I'm about to do a plot with confidence intervals. So now rerun that. Now, in your graphing block, what do you need to change? That's what you need to change. You need to change the data file. There you go. Now, everything else can stay the same because just go in here, add another line. But between CI plot and graph 1, just go to the front there. Yep, hit return. Now go type CI plot and run it. So it gives you the same thing. And you see that it gives you the same variables. You still have treatment and you still have transdat. So you don't need to change anything else about this. Now run that. Now you have means, right? You have a mean for the control, 2% glucose, 2% fructose, 1-to-1 glucose, fructose, and a 2% sucrose. But what does it lack in order for us to see if these means are actually different from one another? It lacks error bars. Okay, so what are the two things that we need to make use of in adding error bars to this graphing block? Okay, so you need confidence interval. So confidence interval is in that data frame. So this CI plot is now a data frame. You've basically created a data frame so that there is now a column within that data frame that is CI. That's the confidence interval. So what is the confidence interval for any mean? It's the mean plus the confidence interval. It's the mean minus the confidence interval, right? So we can add to your aesthetics statement here, we can add y min, which is the minimum value, equals transdat minus CI. Because it already knows that you're working with the data set CI plot. And you can add y max equals transdat plus CI. So add those to the aesthetics. And for those of you following along at home, look at your own script and see if your own script resembles what Hayden is doing. And if it doesn't, make edits to your own script. Yeah, okay. Now run that. Oh, sorry. Oh, you're still doing, sorry, you're doing Ymax also. This is the problem with making your text bigger. It runs you off the page sometimes. If you want to see everything in the same window, you can go after any comma anywhere in here and put a return, and it'll just tab it over. But that's just the symbol. It's just indicating to you that this is all one statement. You've just given it a return so that you can see what you're doing. Now run that. Oh, it hasn't changed. The darn thing has it. So what do we need to add to our graphing block to get error bars to come up? What is geom underscore error bar? Yep, geom underscore error bar. And it's all one word, right? If I'm recalling correctly. And then for right now, just put open parentheses out in front of it. And what's the other thing that you need to do to connect to this section of code to this section of code down here? You need a plus. Okay, now run that. Yes! You have done it. You have made a means graph with error bars. And what you can see is what we kind of already knew because we've already run the data. We knew that control had, interesting, because we did the inverse, the things with the lowest value of transdat are the fastest growing. So when we ran transdat, we have to reconfigure how we think about things. Control grows fastest, 2% sucrose grows next fastest, and these three are all growing the least fast of all of them. And you can see that because this mean doesn't fall within this confidence interval. This mean does not fall within this confidence interval. And neither of these means fall within any of these confidence intervals. So we can visually see, this is one of the nice things about a 95% confidence interval. 95% confidence intervals are inferential. So when we talk about something being inferential, the 95% confidence interval has meaning in terms of what a statistical test would tell us about whether or not those means are different. And so one of the reasons that I like plotting 95% confidence intervals is because the audience of the data doesn't have to think that hard about what those error bars are showing. Imagine if you were to plot standard deviations. And actually, this is a constant struggle that I have with senior research students in chemistry and biology when they're presenting their data. If you plot a standard deviation, that thing might be really wide. But in my head, when I see that you've plotted a mean plus or minus a standard deviation, I have to do a bunch of mental gymnastics. I have to say, oh, well, standard deviation, I have to remember what your sample size is because in order to get the standard error, I have to divide by the square root of n. So then I know that that's the standard error. And then based on n, let's say that you have an n of like 3. If n is 3, that means that the t-statistic is down around 4 or so. Then I have to multiply that 4 times that standard error. I have to do all of this in my head before you move to the next slide so that I can ascertain whether the thing that you told me was different is actually different. Whereas what they could do is just plot a 95% confidence interval, and I can tell at a glance whether the differences that they are showing me are actually different. Because that's the nature of what a 95% confidence interval does. Did the rest of you get a graph that looks something like this? Okay, good. All right. We can pretty this up. So we can, for example, change the size of these whiskers on the error bar code. So you could put size equals 0.1. So just try that in the parentheses. Size equals 0.1, run it again. Oh! Why is that not right? All it did was it changed them from black to gray. Oh, it's not size, it's width. Sorry, width. I'm losing my mind. So that made them not these big, fat, ugly things. You can go into Geom point. You can change the size of the point. You can change the style of the point. You make it a filled point. You can change the color of the point. You can change all these things. In the open parentheses section, it's going to choose a size that is appropriate to your figure, and it's just going to go with the default black, but you can change anything about that. I oftentimes will want to color points different colors. And so in the aesthetic statement up here, you can also define what color things are. So I will use, I think it's style 21. If you go onto the internet and look for ggplot templates, it will show you what different colors are and what their numerical codes are for it. It will also tell you the different types of markers that you can have. Style 21 just happens to be a filled circle with a border on it, and you can define what color the border is and what color the fill is. So if you had 5 different treatments and you wanted to color each treatment a different color, you could, in the aesthetic statement up here at the top, you'd write color equals treatment, and it would color each treatment a different color. So you can pretty up your figures in all kinds of ways. You actually spin yourself into hours of wasted time just trying to make your figures pretty. In the same way that I've shown you in the past how you can actually replace these things that are coming directly from your data file, you can replace these with labels that are more aesthetically pleasing. Using ScaleX discrete. So one of the things that we could do is, sorry, it's not style, it's shape equals 21. This is a filled circle with a border. And then, for example, scale x discrete. And then in the parentheses, labels equals, and then concatenate. And then inside the parentheses, you put whatever labels you want. So in quotes, you might put control, comma, and then in quotes, you might put 2% glucose with a space between the percent sign and the glucose and capitalizing glucose, 1% glucose, 1% fructose, once again with capitalization, and 2% fructose goes in next, and then 2% sucrose, and then close that all up with a second parenthesis. If you do this, if you want to try doing this right now, did you guys do this in yours? For those of you who didn't, try this just right before Theme Classic, right in here. Okay, and now it's got this irritating grid. Why did that grid reappear? Go out to the end of scale x discrete. What did you not put out there? So it's not linking. It's not linking your formatting things. So now it has control, 2% glucose, 2% fructose, 1-to-1 of glucose and fructose, 2% sucrose. You could also then change your angle from 90 to just get rid of angle altogether. Run that again. And now they're all in a line, and you don't have to turn your head to read them. So there are all kinds of ways in which you can play around with how your figures appear. When you're writing a report for this class, or when you're writing a report for anything, one of the things that you'll want to do is you'll want to make the figures in that report consistent over time. So one of the things I also do in my scripts is Hayden, copy the theme part here. Copy those. Go up here above CI plot, put an extra line, and just assign yourself a theme. So you might do something like TH assignment operator, and then put in those two theme statements. Yeah, don't use theme because theme is a command within R. Yeah. Just copy those in. Now run that line. Okay, and all it did was it ran it. Put yourself in a line here. Now type in TH. Yep, now run that. So when you ran TH, it gave you a bunch of things, and you can see that the only thing that it has paid attention to, for some reason, angle is still 90. Well, that's weird because you didn't assign that. Anyway, it's just telling you what your theme is. Now delete these two lines and the plus before it, so backspace. Yep. So now run your graphing block again and then produce the graph. And you can see your theme is gone now. Now go back over to the end of this line. Plus. And then go to the next line. Now just type in TH. Now rerun your graph. Now your theme is back. So theme statements can eat up a lot of coding space. And if you have to recode all that theme stuff over and over and over again, you're just spending a lot of time typing the same thing over and over again, especially if you're going to be producing a number of figures as part of a long, drawn-out sort of analysis that you're producing for someone. You can just specify what your theme is at the beginning, and then for every graphing block that you produce, just tack that theme on at the end of that. Save yourself a ton of time, and you'll have nice, standard-looking graphs that look nice and clean and consistent throughout the entire report that you're generating. So once again, just kind of a shortcut way of doing things from the standpoint of theme statements. Hayden, unshare. Good job. Thanks for doing that. Let me share my screen. So you can see that I have a live coding version of my script, and then I have my script that I generated for this prior to ever walking in here. Why? So two things I want you to pay attention to is you can see that my script has a lot of annotation in it. And then the other thing that you will see is that my theme statement for my graphing block is gigantic. And so imagine having to type that over and over and over again. Better to just throw that into a theme command that has an assignment operator pointing it to something shorthand, and then you don't have to keep typing that thing over and over again. Because I've done things like I'm giving it a title, so I'm controlling what the font size is of the title, controlling the font sizes of all of the elements of text in the figure. I'm also then controlling how the thing appears. And so if you're going to be doing all of that, it'd be nice if all of your plot titles were the same size and in the same font. It'd be nice if all of your X and Y labels were in the same size and in the same font, et cetera, et cetera. So here it's in the graphing block, but you'll see in later scripts that one of the first things that I do in a script is I just define what my formatting block is like, and then I use that throughout the rest of the script. So any questions about that? Everybody get a decent looking figure out of that exercise? Do you guys all feel like you would be confident if I gave you a new data set and said, analyze this data set, you would be capable of testing the underlying assumptions for an analysis of variance and running an analysis of variance? Okay, good. Because in your PowerPoint, thrown in here right after the P example, there's another example. And in this case, maybe I should just blow this up so everybody can see well. In this example, this is the number of ticks taken off of 4 different mammalian hosts. And this is different from the P analysis in that you have different sample sizes. So if you were operating this by hand, when you calculate the sum squares among hosts, you would have to weight each of those sums of squares for the sum squares among by sample size. So it has the added complication of different sample sizes. In the PowerPoint, it's worked out for you. It's worked out. Whoa, that's not worked out. In the PowerPoint, it's worked out for you. So it gives you the means and all this stuff. It's the exact same kind of spreadsheet that we generated for the ANOVA of the P analysis. So what I want you to do for practice, just to practice once again, doing ANOVAs is for Friday. I want you to take the ticks on host data set, do all of the calculations yourself. You can do them by hand. You can do them on paper if you want, although that's total pain in the butt. But then the other thing that I want you to do is I want you to put this into a form that is analyzable by R and write a script that will import these data, check the residuals to see if you have differences if you deviate from normality, check the variances to see if you have variances that are different, conduct the analysis of variance and produce a meaningful graphic showing the means and confidence intervals of these things. It's clear from the p-value that there are differences between the different hosts in terms of the number of ticks that live on the different hosts. So it would be meaningful to show what those differences are, and you can do that with that. So you have kind of a basic functional script that you're currently operating off of. Adapt that script to a new data file and do the analysis. Once again, just to give yourself practice with scripting. But also work it out by hand. And once again, it's been worked out in the PowerPoint so that you can always check your work. So rather than work through that in class, what I want to do is move on to another set of ideas. So in ANOVA, there are 3 different models kind of based on the nature of the treatments. And this is kind of esoteric, but it is something to think about because it does change the analysis in some cases. So one type of analysis views the treatment levels as fixed. And when I talk about a treatment level being fixed, what I mean is that the treatments basically constitute all the possible forms of that treatment that are out there. And so rather than a random selection of possible treatments, the treatments are actually treatments that you are interested in because those are the treatments that you are interested in. So in the case with the P's data set, you, the researcher, or whoever the researcher was actually interested in the effect of these sugars in these concentrations on plant growth. They weren't interested in all sugars and their effects on plant growth. They were interested in only these particular sugars in these particular mixtures and concentrations. That would represent a fixed effect because there was a specific reason for choosing those individuals. In the tick data set, the researchers just went out into nature, found a bunch of hosts, found four rodents, picked up the rodents and said how many ticks are on those rodents. They weren't interested in those specific four rodents. They're interested in rodents in general, and they just randomly selected four rodents from the entire population of rodents that was out there. This is what makes this situation a random effects model. So when we go back down here, we have fixed effects and we have random effects. And so one of the things that determines what model type you are in is whether you are dealing with treatments that are fixed effects, treatments that are random effects, or you can have some cases where you have two treatments that you're looking at. You have one treatment that is fixed and one treatment that is a random effect, in which case that's what we refer to as a mixed model analysis of variance. So these are the things. A model one is where all of the treatments in your analysis are fixed effects. You have model two, where all of them are random effects, and then you have model three, where some of the effects are random and some of the effects are fixed. You actually don't have to worry about this with a single factor ANOVA because there's only one treatment. But this becomes important when we start doing two-factor ANOVAs and higher order ANOVAs. It's just something to think about. When somebody comes to you with a data set that they want analyzed, one of your first questions should be, are these treatments you were interested in for a specific reason, or are these treatments just a random collection of things from this broader population of this treatment that you're interested in quantifying? That then tells you whether you're going to be calculating things using fixed effects or random effects models. When people come to me with data that they want analyzed, the frustrating thing for them is that the first session that I spend with them, and usually it takes 2 or 3 sessions of spending time with them, talking to them about their data, the first session is just me asking them a ton of questions about their data. And then I'm like, okay, we're done. Leave your data with me. I'll work through things and we'll schedule another meeting. And they're like, but I thought we were going to analyze the data today. I'm like, no, it's just me figuring out how you think about your data so that when I go and look at it, I know what your thoughts are about how you want me to treat those data. And so they're very frustrated because the first session is just me peppering them with 1,000 questions about their data, what they did, how they gathered it, what the data mean to them, et cetera, et cetera. And then they walk away and they don't have what they came for in theory, which is a data analysis. But knowing those things about their data tells me how I should go about analyzing the data. And without that knowledge, I'll produce an analysis that might not actually tell them what they're actually asking me to tell them. And so this is just one of the many things that you might ask somebody. I assume that as data scientists, you guys are going to be out there doing data analyses for other people rather than out there actually collecting data yourselves. If you're collecting data yourselves, you think about all these questions before you go and collect your data. If you're receiving data from someone, you don't know what thought processes the person has gone through to arrive at those data and how they were collected, and so you need to get a handle on that. So that's just one small aspect of it is figuring out whether it's a fixed or random effect ANOVA. When we get to two-factor ANOVAs, we'll discuss how the calculations vary depending on whether it's a fixed or random effect ANOVA. So these assumptions are the assumptions that we've already talked about. You will get tired of seeing these assumptions. Once again, keep in mind, these two assumptions are assumptions that you presumably take care of before you ever go out and gather the data. These are things that you make sure in the collection of the data that you have satisfied these assumptions. These two assumptions are assumptions that you have no control over. You only know that you're violating these assumptions after you get the data. But of these two things, the homogeneity of variances assumption is the most important one because it's the one that really affects your ability to interpret differences. Turns out parametric methods like analysis of variance are really robust, meaning that they're not affected very much by deviations from normality. It has been shown a number of times through simulation studies that deviating from normality is really not that big a deal. Why? Why does it not matter if your sample data deviate from normality? Are you making inferences about the sample data, or are you making inferences about the sample mean? You're making inferences about the sample mean. What do we know about the distribution of sample means? It's normally distributed regardless of what the underlying population is because of what concept? The central limit theorem. So that's one of the reasons that the normality assumption, even though it almost always appears as the third thing in this list in any statistics textbook, it's actually the least important because of the central limit theorem. Now, in order for the central limit theorem to be applicable, you need to have sample sizes that are relatively large, more than 20 or 30. But once we've even shown with your simulations at the beginning of the semester that even with sample sizes as low as 10, your data begins to appear normal with even relatively low sample sizes. So this is way less important than this one. This one will bite you in the butt every time. And so as you go through and you're doing the assumption checking, you should definitely pay attention to the um, result of the Levine's test, the one that tests for homogeneity of variances. So one of the other things, so this is the data for the hosts. This next figure in the PowerPoint is the deviations, the absolute value of the deviations of the actual observations versus the mean for each of these. So if you did an ANOVA on these things, it should give you the same result as the Levine's test. So you can once again remind yourself that a Levine's test is only an ANOVA done on the deviations, the absolute values of the deviations from the mean for each of the samples. And that's the result of the homogeneity of variances test. And you can write within your script, you can demonstrate to yourself that that's actually, once again, true. So what I want to talk to you about next, though, is, so we did an ANOVA. We just did an ANOVA on this P growth example. And we found that there were differences. Because we had a p-value that was, what was your p-value that you generated for this data set? Was it something like this? 2 times 10 to the minus 16th? 2 times 10 to the minus 16th is the lowest p-value that R will produce. So your actual p-value is probably something lower than this. This is just as low as R goes. So what this means, once again, what is P? P is the observed what? What is alpha? Type 1 error rate. This is the type 1 error rate that you set for making decisions. What is P? It is the observed type 1 error rate based on your data. So what it's basically saying is, if you say one of these treatments is different from the other treatments, your chances of being wrong in saying that are this low. It's basically saying there's a difference there. Now, does the ANOVA tell you what's different from what? Just looking at the ANOVA. Yeah, why does it do that? This is the P's data set. We got an amazingly low p-value. Does this analysis of variance tell you which treatments are different from which treatments? No, it just tells you that there's at least one difference in the data set. Now, we know from looking at it already in some detail that control is different from everybody else. Sucrose is different from these three, and sucrose is different from control. But we only know that because we graphed the data and looked at the 95% confidence intervals. That's the only reason we know that. All you know from this is that a difference, at least one difference, appears in these means, among these means. It doesn't tell you which one. So then the next question is, after a significant ANOVA, after you found a significant analysis variance, you know that there is at least one difference in there. How do you go about figuring out what things are different from what other things within these, among these treatments? And so if the ANOVA was not significant, I'm having trouble writing today. You're done. We found no differences. There are no differences. So there's no point in doing any what we call post hoc comparisons, after the fact comparisons, to look at what those differences are, because there are no differences. So if P is greater than alpha, whatever your alpha level was, which that means in most cases P is greater than 0.05, there are no differences, so you don't go looking for what things are different from one another because there are no differences. But if your p-value is less than alpha, then it might be useful to know what is different from what. And there are procedures for doing this. La 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 la. So there are two ways of doing this. One way of doing this is you have a set of what we call planned comparisons. So in the P data set, we had a control where there was just water. We had 2% glucose. We had 2% fructose. We had 1:1 of glucose to fructose, and then we had 2% sucrose. So if you study chemistry, you know that these are simple sugars. And this is a double sugar. Okay? So these are simple sugars. This is a double sugar, but this is a double sugar that is made by bonding glucose to fructose. This is basically table sugar. It's a molecule of glucose bonded to a molecule of fructose to make sucrose. And so they chose these sugars. They weren't random. They were chosen for a reason. And so they kept the concentrations always the same, 2%, 2%, 2%, 2%, compared to a control. And they just varied whether that was 2% of a single simple sugar, 2% of another single simple sugar, 2% of two single sugars mixed up into a solution together versus 2% of a double sugar that was those two single sugars bonded together. You see the logic of why they're doing things this way. So the people who did this study had a set of ideas in mind. And so one of the questions that they might have is they might just want to know, are sugars different from the control? Might be one type of comparison that they might be interested in. But they might also be interested in, are simple sugars different from double sugars? They might also be interested in, are simple sugars that are all the same different from simple sugars in a mixture together? These are all logical kinds of questions that these researchers might have about their data set after they see an analysis of variance that is significant. But they would have had these ideas before they ever did the experiment. Actually, probably one of the reasons they did the experiment is because they have these kinds of questions in mind. That's what we mean when we talk about a planned comparison. A planned comparison is a comparison that was anticipated prior to the analysis being conducted. In many cases, prior to the experiment being done, these were the types of comparisons that they wanted to make. And so we can code these things as contrasts. So for the control versus the simple versus the sugar contrast, this might be coded as a 4. These would all then be coded as -1s. Your contrasts always add up to 0. And what it basically is doing is it's setting up 2 new treatments. Instead of 5 treatments, you have 2 new treatments. One treatment is called 4. The other treatment is called -1. They all add up to 0. This treatment that looks at simple sugars versus a double sugar doesn't involve looking at the control at all. You don't really care what's going on with the control for this comparison. So it would be coded as 0, and the contrast here would be -1, -1, -1, and 3. Once again, that adds up to 0. That would be another planned comparison, another set of contrasts to define this planned comparison. The planned comparison of simple sugars versus a mixture of simple sugars would have control coded as 0, sucrose coded as 0, and it would have -1, -1, and 2. Once again, these numbers just form groupings. They're essentially treatment identifiers that tell the computer program, I'm going to be comparing these things with that thing. And once again, all of your contrast should always add up to 0. Now, the thing about planned comparisons is that you only get as many planned comparisons as you have treatment degrees of freedom. So in this case, we have 5 treatments. Treatments, right? 1, 2, 3, 4, 5. Yeah. So we only get 4 planned comparisons. And when you're done with those 4 planned comparisons, that's all the planned comparisons you get. It's all that's allowed. And I'll demonstrate this to you probably next time. R won't let you do any more than 4 planned comparisons. It stops you at 4 planned comparisons because you only have 5 treatments. And so we have, right now, we have 1 planned comparison. We have a second planned comparison. We have a third planned comparison. We can make another fourth planned comparison if there was a planned comparison that we were interested in. So for example, we could be interested in whether there are differences between simple sugars that are single sugars versus a simple sugar that is um, a mixture versus this one. And so that would be another comparison that we could make if we had that comparison. Another way of doing comparisons is just to do unplanned comparisons. And unplanned comparisons implies, okay, I did this experiment, but I didn't have any a priori or before the fact idea as to what I wanted to compare to what. And I'm really just interested in what things are actually different from one another. And there was no structure to my thoughts about what might be different from one another when I went into it. And so these unplanned comparisons, what they generally try and do is they do all paired comparisons. But they do this in a way that controls what we refer to as experiment-wide alpha level. So it does it in such a way that you don't exceed the alpha level of your entire experiment, which in this case is 0.05. So remember, back at the beginning of this conversation, we had control, we had a control versus glucose versus fructose versus glucose, fructose versus sucrose. And remember back at the beginning of this conversation about ANOVA, we basically said, well, why can't you just compare glucose, control to glucose, control to fructose, control to the glucose fructose mixture, control to sucrose, then compare glucose to fructose, glucose to the glucose fructose mixture, glucose to sucrose, compare fructose to the glucose fructose mixture and to sucrose. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. I've missed one. There should be 10 comparisons. Oh, sucrose has now been compared to everything except glucose fructose. So it's glucose fructose compared to sucrose. So I could do 10 t-tests, right? But for each of those t-tests has an alpha level of 0.05. And so if we add those up, 0.05 for that comparison, 0.05 for that comparison, 0.05 for that comparison, 0.05 for that comparison, for this entire set, we get to an alpha level of 0.5, which means we have a 50% chance of saying that something is different when in actuality it's not. So what we want is we want a method for doing this that keeps our alpha level at the level that we wanted it at the beginning. And doing a lot of t-tests isn't how you do that. You do that with some sort of unplanned comparison that has been designed to compare all those things to one another while keeping your experiment-wide alpha level at 0.5 or below. And people smarter than all of us have done this. So we will use the Tukey-Kramer test to accomplish this. It's the most kind of robust test for doing this. So this is the way you go about calculating it. The minimum significant difference is what this is called. So it's called the honest significant difference or minimum significant difference test. And what we have to do is we have to calculate what the minimum significant difference is. So the minimum significant difference is the critical value times the standard error. And the way you calculate the standard error is you take the mean square within, that mean square within value from the ANOVA table, multiply it times 1 over the sample size. And so this is easier to do when sample sizes are the same than when sample sizes are different. And then you divide that by 2, take the square root of that. That is the standard error. And then the critical value you get from a table. So on your tables, there is a statistical table. And the statistical table is the critical value for the studentized range test. So this is what you would go and look at. And it relies upon two pieces of information. The number of treatments which in this case is 5, and that's what goes across the top, and V is the error degrees of freedom. Which you can take from the ANOVA table, but you can also calculate the error degrees of freedom because it's the total observations, big N, minus the number of treatments. So in this case, we have 50 observations, and we have 5 treatments, so error degrees of freedom is 45. So if you go in this table to 5 numerator degrees of freedom on the top and 45 degrees of freedom down the left-hand side, you find that 45 is not there. So this table is useless. No, this table is not useless. We can extrapolate. We can take the degrees of freedom at 40 and 60, which are 4.039 and 3.977. We can take the average of those. That would give us the degrees of freedom, or the value of this estimate that we would have at 50. And then we could take the answer at 50 and the answer at 45 and average those. And it would give us the estimated value of this statistic at 45, and that ends up being 4.028 something. So you can do that math. That's simple math. Just add the two things together, divide by 2, then take the answer from that, add that to 40, divide by 2, and that gets you to 45 degrees of freedom. So 4.02 times this thing for this particular data set in the P's is 0.7389. Your minimum significant difference is 2.97. So that's the difference, that's the minimum significant difference, 2.97, that you would compare all of your differences to. And so one of the things that you can do is you can make a table where you have the minimum significant differences, which are all 2.97. They're all the same because in this case, all of the sample sizes are the same. So the minimum significant difference is going to always be the same. And then you just ask yourself, well, how different is the control from glucose added? Well, that's a difference of 10. That's a difference of 11. That's a difference of 12. There's a difference of 6, difference of 4, 1.3, 1.0, 2.2, 5.9, 6.1. So in this case, control is different from everybody else because the actual difference you observe is bigger than the difference that you calculated. 2% glucose, though, is not different from 2% fructose. 2% glucose is not different from the 1-to-1 mixture of glucose and fructose because their differences are smaller than the differences that are calculated. Okay? So this is how you would do this by hand. So my advice is go home between now and Friday, work through this calculation for yourself using the table that you have and the data that you have from the ANOVA table to make sure that I calculated the minimum significant difference correctly. On Friday, the first thing that we will do is I'll show you how to run a Tukey's on a significant difference test. Other assignment between now and Friday. Now you're like, oh my gosh, what does he expect me to do between now and Friday? So I want you to run the tick data. I want you to run the honest significant difference data for the P data. And I want you to do a little bit of research online as to how one accomplishes a Tukey test within R. And that's where we'll pick up on Friday. Questions? Yep. 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 And if you have troubles with that between now and Friday, make an appointment, come see me. Yep.